So good afternoon, everyone. Welcome. Today, the Atom Seminar has the great pleasure to welcome Professor Amparo Galindo. She majored in chemistry from the Universidad Complutense de Madrid and completed her PhD in physical chemistry at the University of Sheffield. Professor Galindo currently works as a professor of physical chemistry at the Imperial College London. Her research interests include the development of statistical mechanical approaches for complex systems and their application to processes relevant to industry. Her goal is to develop fundamental approaches to contribute to the understanding and experimental systems, with a special focus on chemical process. So once again, welcome, Professor Galindo. Thank you so much for being here, and please feel free to share your screen and start your presentation.
Okay, let me try this. Okay. You have my screen?
Yeah, that's perfect.
Okay,
Yeah.
Can you hear me okay?
Yes.
Okay, so then I'll start. Thank you so much for the chance to speak to you today. Looking at the list of previous speakers, I am very honored to have been invited, and it's really a pleasure to be here today, and I hope you enjoy the talk. So I'm going to, as the title was saying, to tell you a little bit about the work that my group has been doing in developing theories and the relations between theories and simulations. And I'll be talking about conformality, predictions, and coarse graining with the SAFT-γ Mie equation of state. Okay, and the slide is not moving. No, I think it takes a little while to load. Okay, so my group, we work in an area that we have labeled molecular systems engineering, and the group as such, we call it molecular systems engineering at Imperial. And as you were saying very nicely in the introduction, the interest that we have is to start with an understanding of molecular level information and taking it to larger scale. So let me get a pointer. There's a pointer. So we start developing theories and studying and developing an understanding of intermolecular interactions and developing molecular models to be able to predict bulk properties, usually equilibrium properties, and when we use computer simulation, sometimes transport properties as well. And then using this to be able to deliver tools for the design of better products and processes. So as you were saying, we start very fundamentally from statistical mechanics. The end goal is to have an impact at the level of delivering better processes, or really better tools for process design. And so the group as such in Imperial collects a nice blend of scientists that have an interest and work in fields related to process systems engineering. Some come from computing, many chemical engineers, and then also chemists and physicists, for example. Okay, and some of the areas that we work on, especially in the area of molecular modeling or supporting the advances of molecular systems engineering from a molecular modeling perspective. Some of the areas we work on relate, for example, to processes of interest in pharmaceuticals, and in particular to the prediction of solubility and partition coefficients of active pharmaceutical ingredients, the prediction of API solubility when pH is changing. We do a lot of work as well on solvent design. So developing tools that allow us to find the best solvents in different scenarios. For example, we have been modeling amine-based solvents for CO2 capture processes, and we are able to have as an input parameters of a process and then find what is the best amine for a given economic performance or separation. We also develop solvents for enhanced kinetics, and we look at how, again, can we find the best solvent for a given reaction or to accelerate the rate of a particular reaction. And also, for example, in the design of solvents for API crystallization and for the improvement of yields of APIs when they crystallize. We, over the years, have done a lot of work related to the oil and gas industry, because a lot of our funding came from this industry, a little bit less so at the moment. And especially in recent years, we have worked on developing tools that allow us to understand saline environments and delivering predictive properties of aqueous solutions in the presence of salt, for example. And then the group does a lot of fundamental research underpinning this goal of delivering, as I was telling you, optimized tools for process design. We do a lot of the fundamental research that allows us to develop these tools. So we work on the development of state-of-the-art equations of state, and in particular SAFT. And I'll tell you more about this during the talk. We work on the understanding of how to best model electrostatic interactions in complex solutions. And we take advantage of coarse graining and the implementation of coarse grain potentials in force fields, so we can achieve simulations of complex systems, aggregation, for example, and also of transport properties. And so there's a lot of things here, as you can see. And today, in particular, I'm going to talk about these three aspects. Most of the talk will be about SAFT and the recent advancements that we have done with a particular variant of SAFT. And then from there, I will also link it to how can we use SAFT to develop coarse grain potentials and to understand, the parameters underlying the force fields. And I will show you some examples of the type of accuracy that we can have in delivering solubility for pharmaceuticals. Okay, so in terms of the workhorse that we have for delivering predictively properties of complex fluids, we use the SAFT equation of state, the statistical associating fluid theory, which stems from a molecular model first proposed by Verdheim and underlying the thermodynamic perturbation theory at first order, which was, as I say, developed by Verdheim. So the proposition is that an arbitrarily complex fluid is modeled as a chain or a flexible chain of tangentially bonded spherical segments that interact via attractive potentials. And this is what you have in the drawing here. So you have spherical segments tangentially bonded in the picture. In addition to that view of the molecule, a number of off-center attractive sites that are drawn in green and red in the picture are added to the molecule. And these are used to mimic hydrogen bonding interactions and to allow pairing and aggregate formation in general. So this is the view, and this is the pair potential implemented. And it was Verdheim who was able to deliver a theory to find the Helmholtz free energy of the corresponding fluid corresponding to this pair potential. And I'm not going to give you details of how the theory works. It's in these papers. In a later work, in 1989, the group of Keith Gavins in Cornell was able to implement the ideas of Verdheim, or the solution, the very beautiful solution that Verdheim provided for an association fluid, to implement it in the form of an equation of a state. And it's, as I was saying, in a paper in 89, and it's when they labeled the equation of a state SAFT. In short, all variants of SAFT can be summarized with the equation that I have down here. And really, what the theory delivers is the ability to write the residual Helmholtz free energy of a fluid, of a chain fluid, of an associating chain fluid, as we have here in the proposed model, as the sum of terms, in which really what we find is that we can find, we can calculate the residual free energy of the fluid, of the chain fluid, if we know the free energy of a reference monomer fluid, so the fluid without having formed the chain. So we need a knowledge of the monomer fluid, the Helmholtz free energy of the monomer. This can be, to give you an idea, can be a hard sphere fluid, a square well fluid, a Lennard-Jones fluid, and the different versions of SAFT implement different references here. And some implement this from a theoretical point of view with analytical expressions, and some, for example, if we discuss, for example, soft SAFT, is an analytical expression that was obtained from computer simulation data. But basically, you need a knowledge of the free energy of a monomer fluid, and also knowledge and expression for the radial distribution function of that monomer unbonded fluid. And again, and this reference monomer fluid, this radial distribution function, ideally should correspond to the one you have in the Helmholtz free energy. So there's a final term here, which is a sum over the attractive sites that we have in the model, which is a function of this capital X, which is the fraction of molecules not bonded at a given site. This fraction of molecules not bonded, I haven't written the expression, but it's also a function of the radial distribution function of the monomer fluid. So the beauty of this theory really is that, first of all, it's extremely compact as you see it there. And it delivers very accurate results. There's plenty of papers demonstrating that in the literature. And the beauty of it is that really all that is needed is these thermodynamic properties of the monomer, much simpler fluid than the chain fluid, obviously, that you're trying to achieve. So with this in mind, in terms of the outline of the talk for today, I'm going to show you, I'm going to do it in two parts. So in the first part, I'm going to be showing you results, well, the work that we did quite a few years ago now, implementing a Mie potential, a generalized Lennard-Jones potential in a homonuclear model of a flexible chain, as I was showing you before. So this is the model that we were looking at before, and we are going to implement a Mie potential. We name this theory SAFT-VR-Mie. And I'm going to show you the type of accuracy that you can expect with the theory. How do we take it, or it was taken in coarse graining, and then some details of the conformality that one needs to consider when using Mie fluids. And in the second part of the talk, I will be discussing the extension that we did a few years later on extending the theory, moving from a homonuclear model to a heteronuclear model. You can see a representation of a heteronuclear model here on the right, which allows us to implement a group contribution approach, which delivers more predictive power. And we will be discussing, do we lose accuracy in this extension to a group contribution idea or not, or how much accuracy do we lose? And can we use this in the context of coarse graining? Okay. So in terms of SAFT-VR-Mie, we developed this approach. I hope you see it in my screen. It's hidden, but okay. We developed this approach now quite a few years ago. And here we have the Helmholtz free energy, as I showed you before. As I was discussing, the key in the theory is having the ability to deliver the Helmholtz free energy of a reference monomer fluid, of an unbonded fluid. And the more accurate you can deliver this Helmholtz free energy and its corresponding G of R, the more accurate the end result. And so we had worked for a number of years with the SAFT-VR equation of a state, where VR stands for variable range, acknowledging that not all fluids follow the same per potential in terms of its range, certainly not, for example, a Lennard-Jones potential, a 12-6 potential. And we first implemented a square well potential of variable range in the early papers. And then in 2013, with Tom Lafitte, who was an excellent scientist, we were able to implement in a lot of detail a Mie potential, so a generalized Lennard-Jones potential. There's a lot of advantages to having a Mie potential as compared to square well. And one, of course, is the fact that it's a continuous potential, so it's much more amenable to simulation, for example. Okay, and in the Mie potential, you have it drawn here. What one is acknowledging is the fact that both repulsions and attractions are important. The detail of precisely how steep a potential is and how slow is the decay of the attractive tail is very important in trying to model accurately all fluids, even if they are non-polar, as we will see, for example, in the case of the alkanes. So in general, in the group, we prefer to take theoretical approaches. So one could have taken the route of SAFT and simulated a lot of the properties of Mie potentials and then parameterized those results of Helmholtz free energy and the G of R to an analytical expression, which, it's definitely a route to go and it can give very good results. But in general, we prefer to follow an analytical approach. And so we implemented a perturbation expansion. So we follow, as we did in the original paper, a Barkenon-Henderson high temperature expansion. And what we did is implemented it to third order. So we have the residual free energy of the monomer fluid as a sum of a hard sphere term, and then the mean attractive energy, and then the second order and third order terms, where beta here is 1 over kT, so the temperature. And so we implement the expressions analytically, and just to show you the type of description that we can achieve for these various terms. For example, the A1 as a function of density, this is for a pure fluid. In the figure, you're looking at numerically calculated, in fact, simulation data with the points compared to the analytical expressions that we implement. And here, 8.6 and 36 refer to the repulsive and attractive ranges of the Mie potential. So as you can see, the term can be described very accurately. If we look at the A2 term, the accuracy is not as perfect, but it still follows the trend. We follow a local compressibility approximation to obtain in the implementation of the theory. And again, the points are computer simulations. And although the agreement is not quite as good as the A1 term, note that in terms of magnitude, as it corresponds to a second order term in the expansion, the value of this contribution of the free energy is 10 times smaller than the contribution of the A1. And finally, we implement the third order term of the expansion, which in our first work with the square well potential we had not done, on the understanding that if the second term is a lot less important than the first term, the third term should not have a big influence on the final answer. But there was a very nice piece of work from the group of Fernando del Rio in Mexico showing that the third term is especially important in densities close to the critical density, and they provide. So we decided to simulate this third term, and we do pretty much a fit to computer simulation data to provide an analytical expression for this term. So once this is implemented, as I was telling you before, if we have the Helmholtz free energy of the monomer, we can obtain the G of R, and then we can implement these terms to obtain a full equation of a state in the usual form of SAFT. And now the question is, how accurate is the resulting approach? And so if we compare first a simple model, so a single one Mie sphere, we have here a comparison of a number of phase diagrams. So we have temperature versus density for a range of Mie potentials, all of attractive range 6, and a number of repulsive exponents from 8 to 36. And again, the symbols are simulation data, and the lines correspond to the theory. The continuous curve is what we're looking at. And as you can see, the theory is extremely accurate in reproducing the simulation data. And here you have a variety of other Mie potentials that have other attractive ranges, 6, 7, 9, and 12, and an impression of of the type of accuracy that you can expect in terms of vapor pressure. So we have here pressure versus density in this figure. I'm just going to check time. Or is it? Okay. Okay, so the result, as you see here, is that we have a high fidelity representation of the thermodynamic properties, certainly of this very simple fluid. We can extend the same thinking to chain molecules. And as you can see, again, the agreement is very good, where we are looking at chain fluids of chain length up to 100. Okay. In moving to treat real fluids, because as I was telling you at the start, really our aim is to develop or to predict the properties of real systems, to then, be able to aid in the development of new processes. So we model the properties of real fluids by comparison to experimental data. The equation of a state allows us to compare, to run fast evaluations, and to take into account wide ranges of thermodynamic conditions. We use experimental data, typically vapor pressure and saturated liquid density, as I was showing you before, where we have very good accuracy with simulation. We use it in a range between 30 and 90% of the critical temperature. We minimize an objective function, which, as you can see, is the difference of pressure and density, and it's a function of parameters for each evaluation. And these parameters are the intermolecular model parameters of the model that I showed you at the beginning. So one needs to find what is the length of the chain M, the size of the segments, the dispersive energy, the depth of the Mie potential well, and then the range of the repulsion, the attraction, and in the case of associating fluids, the numbers of sites and related energies. So let's see how accurate the results are compared to real fluids. What we find is that the equation of a state can deliver very, very good agreement with a broad range of thermodynamic properties of fluids. So in the top panels, we're looking at the properties of alkanes from methane to dodecane, the pressure and the density. And in the bottom panels, we have small molecules, as mostly small gases. And you can see that the agreement is very good in all of the cases. These are the types of results that we can expect for water. So this is now an associating fluid. Anyway, this is water, where we're looking at isobars and also heat capacities. And it's interesting to start looking at some derivative properties, like the heat capacity, which are not easy to obtain accurately with many equations of a state. In fact, it's critical to implement Mie potential, so to have the ability to tune the repulsive range to be able to obtain this type of agreement for derivative properties. And in fact, this is what we have here. So again, as I was telling you before, it's essential to implement a Mie potential. This was shown in a previous paper to the one we published, that this is essential to obtain good derivative properties. And here we're looking at CP, speed of sound, for example, for 2 example fluids for you. So far, what have we learned? We have an equation of state in the form of SAFT-VR-Mie that delivers, as I showed you in some of the comparisons before we looked at real systems, we have a theory that delivers comparable accuracy with computer simulation. If you remember the graphs, the theory and the simulation were practically indistinguishable. The difference is that in an equation of state, we have a straightforward and fast way to develop models for real fluids and mixtures. So the evaluations are extremely fast and we can fit the properties and obtain parameters very, very quickly. Okay, so this is what I was saying. So we adjust the model parameters to experimental data and we can do this very quickly. And we can deliver experimental properties very quickly. Now, the mapping that we have done, the molecule to bit mapping is entirely arbitrary. So each of these spheres that we represent may correspond to one CH3 group or CH2 group if we're talking an alkane, or may correspond to 3 CH2 groups. And you can see where I'm going with this. So in terms of coarse graining or developing force fields, we have a way to develop these force fields very quickly. So it's equally easy and fast to determine parameters for united atom models where one bit is one CH2, or for coarse grain models where one bit typically in most of the work, if you think of the Martini force field, is 3 or 4 heavy atoms. Okay. The parameters are implemented in the equation of state, and then we can translate them very easily to computer simulations. And we tested this, and I will show you those results later, actually. Yeah. So before I show you the results, just to mention that this, the use or the importance of implementing a Mie potential in simulation had been discussed also previous to our work in the equations of state. So there had been works from the group of Mike Klein, for example, and also the group of Jeffrey Potov investigating the Mie potential in simulation. And they had already reached the conclusion, this is from a paper of Jeffrey Potov, comparing the properties of ethane. So we're looking at the vapor pressure in logarithmic form, so a Clausius-Clapeyron plot versus the inverse temperature. This is ethane, and if you see the various types of symbols that we have here correspond to different ranges of potential, okay? Of the repulsive part of the potential, the attractive part is always 6 in these calculations. And we note the line is the experimental data, that is the circles and diamonds that give the best agreement with experimental data. And these do not correspond to an exponent of 12, but an exponent of 16 and 18. So indeed confirming that the 12-6 potential may not be the best choice for best accuracy, even for fluids like alkanes, which are clearly non-polar. Okay. And they mention how the best agreement that one could have had with the Trappe force field, which is a 12-6, would have been the asterisks, the stars. And you can see that they are a lot further from the experimental data, which is the symbol. So following this idea, we published in 2011 with Carlos Avendaño, that I noted also spoke in this seminar, so he might have shown you these results already. We proposed a coarse grain potential for CO2, where we represented the molecule as a single sphere, just trying to test this idea that we could use the equation of state to propose a simple or a coarse grain force field. So we take experimental data of CO2, we use the equation of state, and we develop a force field potential based on a single sphere representation, non-polar, no charges for CO2. We run, minimize the objective function that I was showing you before and determine the parameters that are characteristic of this model. So potential depth, the size of the sphere, repulsive range 23, attractive range 6.66. And with this, we are able to simulate the properties of CO2 and compare them to experiment and indeed to the calculations, the analytical calculations of the theory. And you can see in the figure that across a range of thermodynamic properties and conditions, we obtain excellent agreement. In the figure, the symbols are the simulations, the solid lines are data, and the dashed lines are the theory. And overall, the message really is that the proposition works. And since it makes sense, since the theory is entirely in agreement with computer simulation, and since the theory delivers agreement with experiment, this had to be a natural conclusion, but it was very nice to confirm it. Now, however, we need to discuss one important detail. The Mie potential incorporates 4 parameters that are fitted, as I was telling you. So epsilon, sigma, lambda repulsive, lambda attractive, as compared to the Lennard-Jones, where if we were fitting with Lennard-Jones, we would have a 12-6 and fit only 2 parameters. So a natural question is to ask, are the 4 parameters really needed? Okay, if we run, we minimize the objective function in the optimization as we were doing before, and we control in detail the repulsive range and attractive range. So we fix these 2 and optimize epsilon and sigma. We can map in detail the objective function of the fluid. And in particular, these are results for methane, but the same would be applicable for CO2. And what we see here, the blue region correspond to the minima in the objective function. So here we have values of the objective function across the area of values of lambda repulsive from 10 to 18 in the vertical and 5 to 7 here. So as I was saying, we fix each of the values. For example, the 6, 12 would be here, and we evaluate the objective function. And as you can see, there is large model degeneracy. So any of these models in the blue region would in effect give you the same error in comparison to experimental data. So first of all, we can answer, why is this? How important is this? And can we, do we really need to be fitting these 4 parameters? Okay, so this takes us to the discussion of conformality of this family of potentials. In fact, with the interest in using Mie potentials in simulation, there had been previous works from the group of Orea investigating conformality in this family of fluids. So they carried out simulations for a range of fluids, as you have here, and plotted reduced temperature, where the reduced temperature is defined as T over Tc, versus reduced density rho over rho c, and concluded that the family of potentials was conformal. And from there, one initially naturally concludes that, well, if these fluids are conformal, it means they're all in effect the same. There is no need to be fitting different potentials. However, there was also previous work to theirs from Hasegawa and co-workers describing the family as conformal with 3 parameters, so depending on 3 parameters and not 2 parameters. And indeed, there's also work from the work of Richard Sadus, where global phase diagrams had been calculated, so including the solid phase, as you see here, and where the results suggest no conformality. You can see here that, choosing different potentials, these are all lambda repulsive 6, the curves do not overlap each other at all, okay? I highlight here, because this will be important in a second, that the units in this diagram at the top and the bottom diagram are not the same. This is TR defined in the conformal space, if you want, of van der Waals, and this is T star, defined usually as KT over epsilon. Okay, so the units are not the same, and we will see the impact of this in a second. So we decided to simulate a range of Mie fluids and see what we found. And for the time being, I'm also plotting the phase diagrams here as T over Tc and rho over rho c. I have them labeled with a star. This can be done in a star or without, because the units cancel over each other. This would be the phase diagram for a 23 repulsive range, 6.66 attractive range. So this is the potential we found for CO2, to give you an idea. If we simulate another potential with attractive range 14.65 and repulsions 8, we find the results in purple, entirely overlying the previous ones. If we do this for a potential 9.167, we find the results of the asterisk entirely overlying the previous ones, and then surprisingly and maybe shockingly, the 12.6 potential. So having told you that it's critical to implement a Mie potential to obtain a high degree of accuracy, why are all these potentials overlapping each other? And of course, as I was telling you before, in this space of conformality, it looks like they are all the same. But when we plot them in real, in theoretical units, let's say KT over epsilon, which is really the parameter that translates theoretical units to experimental units, not all 4 fluids are the same, first of all. However, we do find that they have split in 2 sets of fluids. So the first 2 potentials do have the same properties. You have them down here. And the second 2 potentials that I simulated find this behavior up here. Okay. So what is happening? We go back to consider the definitions, the original works of Guggenheim on conformality. So the definitions are, these I followed from the papers, are given usually like this. So in a 2-parameter conformal state model, the underlying assumption is that, first of all, we're dealing with a spherical fluid. I've told you this before. Only repulsive and dispersive forces are important. We all agree on that. So we have 2 scales to worry about. One is a scale of energy, and this is the scale that reduces temperature, and the other is a scale of distance, and this is usually the scale that reduces volume or density. And we use this to relate theoretical properties to experimental properties. Okay, so if we can find 2 or more systems in which we can write the free energy in reduced units, and we have the same expression of free energy, this means that the Helmholtz free energy will be the same. And that if the Helmholtz free energy is the same for those fluids will have identical macroscopic thermodynamic properties. Okay, and so this is very important. It would mean that we don't need to be fitting different parameters for them because they are exactly the same fluid at a theoretical level. So we went back to our expression of the Helmholtz free energy that I showed you early on in our Mie potential, and to the expansion, the high temperature expansion that we have. We make a number of approximations to be able to have an analytical expression for the equation and to simplify the various parameters. So in terms of the mean attractive energy, we write it like this. And then if you notice here, we have U1 would be the Mie potential. We can integrate it. And as long as we integrate, the problem here is the G of R. But if we integrate it in a mean field approximation, I can find a very simple expression, which is a function it's a function of epsilon, sigma cube, which notice that we will use this to reduce the temperature and the density, and a parameter alpha, which comes from the integration of the Mie from sigma to infinity. And alpha is a function of the attractive range of the potential and the repulsive range of the potential only. This C is a constant. It's also related to lambda repulsive and lambda attractive. So writing it in different units, we find that it's possible to write the free energy of the system as a function of reduced temperature and density and only 1 parameter alpha. So what we find is that to a first order of expansion, assuming a mean field fluid approximation, the parameter alpha defines Mie systems of equal free energy at given T and ρ, which is the same as saying describes conformal fluids. So really what it's saying is that in the Mie family of fluids, we do not have 4 parameters to fit epsilon, sigma, lambda repulsive, lambda attractive. It's really 3 parameters, epsilon and sigma, and 1 parameter alpha. Typically what we do in fitting or in developing models, what we have done is to fit the attractive range to 6, since this comes formally from the theory, in the development of the Lennard-Jones potential. So we fix the lambda attractive to 6 and we fit the lambda repulsive only, but equally one could fit simply sigma. So let me show you that, of course, the 2 fluids that I showed you before, the numbers were a bit unusual because they corresponded, I calculated from the 12.6 what would be the corresponding conformal fluid if I made the repulsive range 7. And what you find using this relation of alpha is 9.16. And then what you find. And I did a similar thing, looking for what would be a conformal fluid to our fluid, our CO2 model, 23.666, has an alpha of 0.52. So using that value, I can also find another corresponding potential that is entirely conformal with the one of CO2. We find conformality in the T-ρ phase diagram. And of course, as I was saying, if you have the same free energy, you have all other properties are the same. So here, for example, you look at vapor pressures and there's entire agreement. And one could do this for all the properties and it would be exactly the same. From here, what we did was map the phase behavior of the family of Mie fluids in terms of this parameter alpha. And we find that then, we gain an understanding of the type of phase diagrams that we have and how the solid phase comes in. And we observe that the fluid range of these fluids decreases as the value of lambda decreases, as the potential becomes more repulsive. And so this, in a way, explains the results that Sadus presented with the solid phase. We found, how am I doing for time? Because I'm always a bit slow. I have 5 minutes, I should be okay. I'll be fast. We found from the study of the solid phase that, as I was showing you before, I'm going to go back one slide, that the fluid range, as you can see, is decreasing as alpha decreases. And so we are going to look at the ratio of the critical point up here to the triple point down here. And what we find is that there's in fact a linear relation between this ratio and the value of alpha. And that's very interesting because if we divide the critical temperature over the triple temperature, this can be done, as I was telling you before, this can be done in theoretical units, which were the previous phase diagrams, or in real experimental units, because the units cancel with each other. T star is kT over epsilon, and it will cancel on the numerator and denominator. And so we have a relation that tells us for a given alpha what would be the range where the fluid is stable, okay, the fluid phase behavior. This is important because many coarse-grained models that have been proposed in the literature, it has been found that in making the potential sometimes soft, which speeds up the computer simulations, but the molecules freeze too soon. So there's some models for water published in the literature that actually freeze at temperatures that are too high. But now we have a way to start with the ratio of the critical temperature to the triple temperature known experimentally. For example, for CO2, this ratio is 1.4. So the triple point is 303 and the critical point is 217 Kelvin. We divide those two numbers and we get 1.4. So if I put 1.4 in this graph, I come here and we find that the value of alpha is the one I was showing you before. And so in fact, by pure chance, almost when we fitted our CO2 model, which we did before this study of conformality, we were actually pretty much very close to the answer. Our model was 23.666, which is the left diamond here. An optimal model in terms of the fluid range would have been this diamond on the right, and it would be a potential 31.6. And the same can be done for water, where we find that the optimal potentials in terms of obtaining the correct fluid range for a fluid would be of the order of 8.46, so really quite soft. And these, in fact, are the types of potentials that you see in the literature for water. Okay, so far, I have shown you how we implemented a Mie potential to a third order high temperature expansion that leads to a very accurate equation of a state. And we've seen how we can link that to develop coarse-grained force fields. And that an understanding of conformality allows us to narrow down what molecular models are suitable for real systems and to understand really how many parameters are important in our equation of a state. Okay, and so as I was telling you earlier, in terms of modeling real substances, if you follow our work, normally we only optimize the repulsive range and we keep the attractive range to 6, and this is usually sufficient for most substances. Okay, in 5 minutes, so this is going to be fast, but I should have time to show you everything. I'll just give you an idea of the work that we have done implementing a heteronuclear model. Okay, so we moved from the implementation of the homonuclear model to use again a Mie potential. So we keep this the ability to fine-tune repulsions and attractions, but implement a heteronuclear model with the intention of developing a group contribution approach. So the proposition is that we can break the molecules into the functional groups, and that from the heteronuclear model, we can implement, the free energy as a sum of the groups that form part of the molecules And if we are able to characterize each of these groups, so this requires quite intense parameter estimation, of course, but as I was telling you before, the equation of state is the calculation of properties with the equation of state is very fast. So this can be done reasonably optimally, let's say. Once we characterize all the necessary groups, we have an ability to predict the properties of any arbitrary system. Of course, on the proviso that the idea of breaking the molecules into their functional groups and putting them back together works. And the question is this possible? Do we lose a lot of accuracy in doing this or not? Okay, so we have worked over the last few years in developing a parameter matrix to characterize all the interactions involving various chemical groups. And this is the paper published in our latest progress. So this is an impression of how many groups are characterized now. And in terms of accuracy, does the idea work? Of course, many of you will know of the UNIFAC equation of state, which is a group contribution method, which in a way shows that this proposition is valid to a large extent. And the question is it also valid within these types of models that are implemented in SAFT, where, as I was telling you, we have flexible chains of segments. So for example, if we look at the mutual solubility of water and alkanes, what we are doing is modeling an entire family, the phase behavior of an entire family based on understanding of three segments, the CH3, the three CH3 spherical segments, CH2, and water. And what we're looking at in this phase diagram is the solubility on the left, or let's say composition on the left, and temperature on the right. And we're looking systems containing oil and water, as many of you probably know, separate in two phases. So we have a water-rich phase and an oil-rich phase. So at the top, we have the solubility of water in oil, and the other points correspond to the solubility of oil in water, which is extremely, extremely low. And you see this here, 10 to the minus 9. So we were able to study the solubility from ethane to decane. We characterize the interactions between these groups based on the solubilities of two systems. And we are able to then describe the properties of the entire family, including these very low solubilities here. Okay. The approach has been shown to be accurate for the prediction of all types of phase behavior, so vapor-liquid, liquid-liquid, and solid-liquid equilibrium, and is also, or can also deliver accurate properties of excess. I will move a bit quickly through this. In terms of our work in relation to the improving processes for the pharmaceutical industry, which is a large part of the activity at the moment in the group, we have demonstrated an ability to predict the solution of simple pharmaceutical molecules. For example, we have ibuprofen here. We characterize the matrix. This is a part of the matrix that I showed you before. We characterize these groups from simple molecules. So the beauty of the approach is that you can predict the properties of any molecule, as I was telling you before, from data of much simpler molecules. So this is an acid, this is benzene, as you can see, and these are alkanes. So you don't need data of the complex molecule, let's say. And we are able to predict the solubility of ibuprofen in a range of solvents reasonably accurate. It's not perfect, as you see here, but in terms of solvent design and in terms of process design, we're interested in having the correct solvent ranking. So it's more important, well, ideally you would want to have full agreement, of course, but if you don't, you cannot achieve that at the moment in a predictive way. What is very, very important is to have the correct ranking as to in which solvent is ibuprofen most soluble. We also study, we have the ability to implement charge groups. So for example, here you have the COO group, and to model speciation in these systems, which gives us an ability to predict pH solubility pH solubility profiles in pharmaceutical companies. And so very briefly, because I know I'm slightly over time, I'll show you how, in the same way that we can go from the equation of state of following a homonuclear model to coarse graining, we can do the same with, in the case of the heteronuclear model. The theory retains agreement with simulation, and it means that we can, in the same way, parameterize models using the equation of state and then implement them through coarse graining in a molecular dynamics simulation. So, sorry, so this I was telling you I had a slide. So the theory stems from the heteronuclear model. We carried it as we did in the homonuclear model through formal statistical mechanics. So we preserve a high level of accuracy compared to the simulations. And so we can use it in simulation. We use the theory to determine the non-bonded parameters of the force field. We're going to look at chain molecules now. Of course, once we have a heteronuclear model, we need to move from a single simple sphere to a chain. So we need to consider not bonded, but also bonded interactions. So we need to be able to say something about bending potentials and torsional potentials. And so in terms of stretching, bending, and torsions, of course, SAFT, as I told you, implements a fully flexible model. So we cannot say anything about that. So we get that information first from TRAPE simulations for the bonded interactions, and we get the non-bonded interactions through the equation of state, fitting to experimental vapor pressure and saturated liquid density, exactly as I showed you for CO2 and for the alkanes early on. And then how well does this work? And as we showed before, this, for example, is N-dodecane. So this is a chain. I hope you can see this here. We model N-dodecane as a chain of 3 segments, heteronuclear. So the end bits are different to the middle bit. And as we saw before, the symbols correspond to simulations and the lines correspond to experiment. The lines correspond to experiment and the dashed line corresponds to the theory. In this first work of dodecane, you can see that we have SAFT model A, B, and C. We compared a fully flexible model to a fully rigid model to a model implementing the non-bonded interactions, which is model C. Okay, you can see that there's no large difference between them. We can discuss that with more time. But the important thing is that we are able, and then we have TRAPE as well for comparison. The important thing is that we are able to deliver accurate agreement with experiment, having developed the force field based on the equation of state. The proposed force field is also transferable to other alkanes. So in these figures here, sorry, I don't know if you see me there or not. In these figures on the right here, we're looking at other alkanes. So we develop the force field based on dodecane, and then we confirm transferability to other alkanes. And not only that, we also confirm representability. So not only can we predict the properties we fit it, if you want, but we can also describe other properties accurately. So here we're looking at viscosity and diffusion for, this is dodecane and C24, for which we found experimental data. And we find, sorry, and you have the experiments and the simulations. The simulations are the stars, and you see the type of agreement that is possible with this force field. We tested diffusion, and again, we find very good agreement with model C, so the model that incorporates indeed the torsions and bending in the potential. Okay, so to sum up, I hope that I have, shown you that SAFT approaches can provide accurate thermodynamic and coexistence properties for complex fluids, and that is important to choose physically meaningful models and to follow a rigorous implementation of the approximations so that we can obtain models that are transferable, predictable, and reliable. Okay, and we have seen that an accurate Mie potential leads to an improved accuracy over the entire thermodynamic space, and that is possible to implement this potential in a heteronuclear model to deliver a predictive equation of state, and also how we can use these types of equations to link to and develop, importantly, coarse-grained force fields that are then translatable over thermodynamic states. Okay, with this, I finish. These are some of the sponsors of our work, and I will leave you with this nice slide of the group, because it's with thanks to everyone in the group that I'm able to present to you these very nice results. And we haven't been able to be together for quite a long time. This is one of our latest reunions on Zoom, and we're hoping to be together quite soon. Okay, thank you.
Thank you so much, Professor Galindo, for your beautiful presentation. It's a pleasure to have you here with us. And we are now open for questions. If you want to ask one, please feel free to enable your microphone or write it down in the chat. So, who would like to ask the first question?
I do.
Please go ahead.
Thank you, Amparo. A very nice presentation and beautiful pictures and results. I will start with the derivative properties. We know that it's hard sometimes to get these correctly. And for speed of sound, for instance, people say, you are not going to get correct because you need some fluctuation information, like you have to have in a model that you have to input some dense fluctuations, dense kind of renormalization, so on. But we saw that very nice result from you, either for speed, sound speed, and also for CP. So how you explain this? Maybe it's the repulsive correction that it's take you for this nice result, is it?
I think so. I don't think that you need, I guess, yeah, so you're talking about this. No, so you don't need, okay, it's a good question that, for example, why is interesting. You see here,
because I want to say that I did renormalization, for instance, and well, with renormalization, maybe you get worse than what you get with correct the repulsive. So maybe it's not a matter of doing renormalization that you get correct.
Exactly. So it's interesting. So the theory is a classic theory, analytical. So of course it does not describe the critical exponents accurately as you would with renormalization group theory, for example. So it's interesting that when you look at the phase diagrams, they look extremely flat. And it's something actually that I queried early on when we were developing the theory. If you calculate the critical exponent of the theory, it's actually 1/2. So it's not a third. This is interesting that, you know, the critical exponent, really, you only notice it very, very close to the critical temperature, incredibly close to the critical temperature. So yeah, so it's a very good point. So, you know, in no way are we predicting critical exponents. It was the work really of Fernando del Rio that shows, you know, this importance of the third order term. And then that delivers this type of agreement close to the critical point, although not in any way critical behavior. So when you do these calculations, you can actually, you don't find the discontinuity, but you certainly are able to predict the CP. You can see how, you know, it comes up and down in very good agreement with experiment. The importance is to have this ability to vary the repulsive range. That is the critical thing to get CP. You will not get it at the critical point because, like I say, it's not renormalization group theory, but, you know, except that point, until you get extremely, you know, precisely at the critical temperature, you can have extremely good agreement.
Have you tested already entropy scaling to calculate viscosity with this approach? Because close to the critical point, have some small change in slope close to the critical point for the viscosity. I don't know if you can get this with the repulsive, or it's a matter of very close to the critical point, you should do something else.
Yeah, I don't know. I'm not sure I understood your question.
No, because if you see the data close to the critical point for viscosity, you see some change in slope. No changing, small change in the slope. So so if you use normal scaling with normal equation of state, maybe you don't get these. At least I could get close to even if you do renormalization, because we test with renormalization to see if it's a matter of doing some fluctuation in densities that maybe you can get this. But
yeah. I haven't looked into that, I have to say. I think the equation should allow you to get closer to the critical point, but as I say, it will not deliver the, universal critical behavior.
Okay, let people ask. If not, I have more questions for you.
So who would like to go next?
Daniela Correia. So, Ana Carolina Coutinho.
I could ask a question if you don't mind.
Please go ahead, Professor.
Hi, Galindo. Amparo, this is Richard Elliott.
Hi.
And so I was interested in your results for the melting temperature trends. I think all of those apply to the spherical perspective, right? So those are just for monomers.
Yeah. Yeah.
So how would you? So my questions are really related to that. How do you go beyond the monomer? So how do you know when to treat a molecule as just a sphere or as a dimer?
Ooh, I'm not sure I understand your question. So you want to know how to extend the theory to treat the solid for change, or?
Well, for the moment, I'm just saying in your theory, so is propane, so I know CO2 is a sphere. You're treating it as a sphere in this graph, right?
Oh, yes. Yeah.
But where would propane be? Is that a sphere also?
Yeah, I understand now your question better, Rick. Sorry. Arbitrary. No, you completely. I think it's so you're talking coarse graining. So when you have to make these decisions a priori of how many beads am I going to use for a given real molecule? Yeah, I think it's what you are asking.
Yeah, where do you draw the line? I know there are a lot of different theories and approaches, but what do you do?
If you're talking our coarse grain potentials, for example,
for the SAFT-γ Mie and exactly what you're doing.
For SAFT-γ Mie, if we're talking the predictive SAFT-γ Mie, we would do propane as 1 CH3 bead, 1 CH2 bead, 1 CH3 bead. Is that your question? If we're talking coarse graining, and you want to say, well, I want to have a force field that involves less than 3 spheres, so I have less interactions to calculate, then that decision to say, do I do propane as 1 single sphere, so 3 heavy atoms for propane, just 1 sphere, or do I do propane with 2 beads, in my view, is arbitrary. And I'm sure you know. And then in the literature, there's plenty of works of people, doing those sorts of comparisons. Or on the reverse, what is the best model of water coarse grain? Should 1 bead include 4 water molecules or 3 water molecules? So that, in my view, is arbitrary. You check it. You check with experiment, and you see which model delivers the best accuracy. And often the answer is it will deliver the best accuracy for some properties and not the other properties. So the final answer depends dramatically on what property you want to study, in my view. Was that your question?
Well, I'm still trying to focus just on the SAFT-γ Mie, what your formalism is, and so.
So SAFT-γ Mie would be with CH3 for propane, CH3, CH2, CH3.
And CO2 though is just 1 sphere.
No, and CO2 in SAFT-γ Mie is actually 2 beads. It's actually 2 groups, 2 identical groups overlapping. So it's slightly non-spherical. Sorry.
Okay. Well then, what's this graph that you're showing of which theory is that? The one with the melting temperatures?
It's SAFT-VR-Mie also, but that's coarse graining, Rick. So this is where I'm confused. If you're talking the coarse graining models, this is a good slide to have this discussion. Molecule to bead mapping is arbitrary. It doesn't matter. There's a unique theory that allows you to go, to say, this is the real molecule I want to treat. And there's a unique theory that says you choose how many bits you want to do, and then you optimize parameters as you decide. This, how many molecules or how many carbon atoms you have in a bit is entirely up to you. So in some of the results that I was showing you, it's just one bit. And then sometimes when we treat real fluids, we do more detailed models. And it's completely arbitrary. It's a unique equation of a state. We only have one.
Okay, so the one that's for this melting temperature plot is not SAFT-γ Mie, that's SAFT-VR-Mie.
Let me go to, are you talking? Oh, sorry, it's going to take a while. It's only one sphere, Rick. So in fact, are we talking this?
Yeah, this graph here. This is what I was interested in.
This is one sphere. It's
so this is SAFT-VR-Mie, not SAFT-γ Mie.
Now, if we're talking one sphere, both theories are identical, if you think of it.
Oh, okay.
Yeah. So it's completely the same. Doesn't make any difference.
Okay, so I guess it's the nature of
theories,
the theory.
In a way, there's only one theory, if you want. There's only SAFT-γ Mie, because in SAFT-γ Mie, there's a parameter. I think you're probably familiar with the theory, no? There's a parameter in SAFT-γ Mie that tells you how much two spheres overlap.
Yeah, there's actually another way of doing SAFT-γ Mie where you can let the bond length be variable. It doesn't have to be tangent.
Basically, if in that theory you make the spheres tangential, be it through the bond length or being because the shape factor is 1, that theory, and all the spheres are the same, that becomes the homonuclear model. So in a way, there's only one theory.
Yeah, so you're using the tangent sphere version of SAFT.
Exactly. And we devised SAFT-γ Mie intentionally to be fully consistent with the homonuclear model. So in fact, that was one of the checks to ensure that it would deliver entirely identical answers for a homonuclear model. And then in the particular case of a single sphere, there's only one theory. It doesn't matter. The names are confusing.
Yeah. So maybe I can nail it down this way. I think you have an implementation of CG SAFT-γ Mie, the coarse grained SAFT-γ Mie. Is that right? It has like multiple, like 2,000 molecules characterized or something like that.
Homonuclear, I think, Rick, are they homonuclear? I think you're talking
something that Eric Muller talked about.
You're talking about bottle SAFT, work that Eric Muller has done. Exactly, that's homonuclear, if I remember correctly. But I haven't done that, Rick, so you'll have to ask Eric. I think it's homonuclear. I think that work is homonuclear.
All right, and so if that's the name to call it, then is propane a sphere or a?
And so I don't know how. So I presume, I don't know, Rick, I don't want to say because I really don't know how it's done. So that's,
Well, okay, so maybe I can just sort of, I'm trying to, nail down the names of things to say it right, but I don't know. And so, but the basic idea I had in mind is this is a nice looking graph, and melting temperatures are really hard to predict. And so how do we go from something that's only applicable for spheres to propane, okay, or benzene, or something like that?
Yeah. So the conformality that I was showing will not hold for the chains, for example. So certainly we have to do it by M. You can see immediately that you're adding one extra parameter in the free energy. So the concept of the equation will go from being conformal with 3 parameters to we need M. So clearly that already. So I would expect that if you could do that, you would get another line, well, I don't know if parallel, but there would be another line corresponding to this one. For any given M, we would have to do, either develop a theory or run the simulations that tells us how do the phase diagram change for each M.
Yeah. And you haven't looked at that.
No. And for example, and would this behavior be linear or not? I don't know the answer to that. I have done work. So in terms of the theory, I think, I can remember. I've done work that you might have seen, extending the thermodynamic perturbation theory, so the same idea that delivers SAFT, to the solid phase. And you can show that you can actually have a very accurate evaluation of the Helmholtz free energy, again, of the solid phase of a fully flexible chain in exactly the same way. I did this work with Carlos Vega a long time ago. The difficulty when it comes to the solid phase and a real fluid is that the TPT1 model implements a fully flexible chain. And in fluids, this idea that we model them fully flexible works. We get away with it, but molecules are in no way fully flexible. So in the solid phase, the implementation of a fully flexible model breaks down. And you calculate the Helmholtz free energy in full accuracy with simulation, but you don't have agreement with experimental data. Yeah. So the model breaks down, not the theory. The theory is fine, but the model breaks down. In the same way, if you want that I was showing you at the end that in coarse graining chains, you do need your bending and torsional potentials. Yeah.
Yeah. I'm just thinking, well, with a dimer, you don't have to worry about that.
No, you're right. The dimer is the only one where you have agreement. You're right. Yeah. And in fact, we showed that in the paper. The dimer, you're fine.
Oh, okay.
Yes, that is very right. That is very true. Yeah.
Okay. Very interesting. Okay. I guess that's pretty much, well, I guess you said, I don't know. So you said the perturbation theory works well for the dimer, but you haven't looked at the melting temperature trend, to see how it lines up.
No. So I haven't checked if, I think it was flexible chains, the theory that we did for flexible chains in a particular scale that I cannot remember, proposed by Flory, it is linear. But it's, it was linear as a function of molecular weight, which I guess is M, not as a function of parameter. That is what we have here, not this parameter. I can send you those papers, Rick.
Yeah, okay. Do you know roughly what year that was? Or 10 years ago?
Yeah, 10, probably more.
Okay, thanks.
It's like yesterday, but it's probably more.
Yeah, I know that feeling. Okay, thanks.
No problem.
All right, who would like to ask a question? So I think maybe Professor Fred still has some questions.
Yes.
Please go ahead, Professor.
Amparo, can you put the solubility data for hydrocarbon more?
Yeah. You're seeing my screen at the moment, no? Are you seeing my screen?
Yes.
This one? Yeah.
Yeah.
Whichever.
At low temperature, you can see a minimum in this data that maybe correspond to the hydrophobicity or hydrophobic interaction. How can we include these in the model? Maybe for the water, it's not a problem of the group contribution. Maybe it's a matter of water model, is it?
Yeah. It's very, you see it there, this minima. So the group contribution does quite well. It's not bad. I think, at least it's turning a bit, but you can see it misses it. Yes, I think we showed, in fact, with a different model, not the group contribution, you can fit it much closer. But I think in the end, like you say, I think it's water. In fact, I have calculations that where if you can parameterize water specifically with a very unusual potential, you can capture this minima. But I think in the end, like you say, it's about really the structure of water close to that minimum. And in TPT1, at this level of theory, we're not accounting for that, for what is happening at that low temperature in water.
So expect that all the problems related with hydrophobicity, maybe you're going to miss some information with this approach.
That is my impression. Yeah. My conclusion, I mean, you can fit it. It has been done. I mean, I have done it. There's a paper by Lourdes Vega showing, so you can tune the parameters to get it, but I think there's something more fundamental than that happening. And I suspect it is, like you said, to do with the structure of water and maybe caging over some of these alkanes. Something is happening that we're not accounting for.
Well, it seems to me that you've left out the A of the SAFT model.
Yes.
Which it's nice if you don't have to include it because the calculations are so complicated. But if you're talking about hydrophobicity, it seems to me you do have to include the association effect.
Yeah. Well, in this model, sorry, because I went very quickly. The model of water in these calculations is associating. Yeah. Oh,
okay.
Yeah. Sorry, no, I went super quick and the picture doesn't, so the model of water has 4 sides.
But there are parameters associated with that?
Sorry? Yes, yeah. So it's a 4 sides.
And those are regressed on the pure water.
Yeah.
Okay. And as we found that doesn't necessarily work when you're talking about mixtures.
Yeah, for example.
Yeah.
For example, yeah. And
I got it.
My sense, to be honest, John, is that, I mean, this model of water where we have, spherical water with the 4 sides does extremely well in many properties. But of course, in the theory of Verdheim, the sides are independent of each other. So we add 4 sides and we simply sum over 4, where I suspect that one will need to go to a next level of theory where one side has some information of the other side. So we can, for example, describe something of the angle, the angularity of water, the direction, that directionality, I think is what we're missing, to be honest with you. That's my view.
Yeah, fair enough.
Thank you. Maybe explain some deviation that you got for some drugs. It was very nice result, but some more qualitative than quantitative prediction. But even though very nice, but maybe if with this improvement you can get better results.
Yeah, I think
I say that maybe it's a water problem. It's not the group contribution. Is it in water or not? It's not solvent. It's not water. Okay.
Yeah, no, these are other solvents. I think here, as you have a lot of groups next to each other, I keep moving this thing out of the way. As we have groups next to each other, as the molecules become more functionalized and more complex, things get tricky, basically.
Yeah.
So, chemistry kicks in. So the groups polarize each other. So, the concept of group contribution is fantastic and it's impressive that we can break them and put them together. But as you have increasing functionality, you lose accuracy. And it's a balance. It's a balance where you say, well, still it gives me an ability to predict at some level. And this is ibuprofen, which we know a lot about, but this could be any drug. So it gives you the ability to say something reasonably sensible of the solubility of a drug that you may want to start considering. If you want full accuracy, you need to move to probably, a detailed model, where you actually fit the molecule that you need and you don't use group contribution. If you're going to develop a process, you will not use this.
Thank you, Amparo. Very nice talk.
Are there any more questions? Okay, so I think we can wrap it up then. Once again, thank you so much, Professor Galindo, for the presentation. It was a pleasure to have you here with us.